Hello, hi everybody again. So today we're going on to the pH of the final solution, right? And I want to emphasize that it's saying the pH of the final solution, not just the pH of an acid, not just the pH of the base when they are a substance alone. Because before we've been calculating what's the pH of hydrochloric acid alone, what's the pH of sodium hydroxide alone. But what about when the hydrochloric acid and the sodium hydroxide react together? What is left at the end? And guys, I hope you can hear that I'm saying the word what is left over at the end. So meaning we're about to look at what is an excess versus what is going to be the limiting reactants. Because every time in acids and bases, I can guarantee you an acid and base will react and something will be left over and the other one is just going to be gone. It will be finished. That will be your limiting reactant. So that's why we need to remember how to solve questions on limiting reactants. So here we've got an example. Hydrochloric acid reacts with sodium hydroxide, forms a salt and water. Now they give us information here. They tell us that initially, and emphasis on initially, right? Initially you've got 3 moles, and I want to write this down. Initially you've got 3 moles of hydrochloric acid, and initially you've got 2 moles of sodium hydroxide. So now what happens? And they also tell you the volume. You've got a volume of 2 of hydrochloric acid and a volume of 2 of sodium hydroxide. And I've drawn that in a picture. I've separated them, okay? I've separated the 2 containers for a reason. Because I want to say that this is my flask where I've got my hydrochloric acid, and this is my burette where I've got my sodium hydroxide. Now what happens is you open the tap and you start bringing in little bits of sodium hydroxide into the hydrochloric acid. Now what happens? These two, now I want you to imagine these are both in the flask now. So let's say all of the sodium hydroxide goes into the flask, okay? Now this is your flask. What you now have inside of your flask is you're now going to have a mixture of your moles of hydrochloric acid as well as your moles of sodium hydroxide. You're going to have both of these things inside here. Okay. But now another thing I want you guys to look at. Imagine if you had, let's say, water in a glass, right? Let's say this is half of water in a glass. Then you add on the other half of the water, let's say you add milk, right? What's happening here is that the volume of the milk and the water together is going to be greater than their volumes separately. That's what's going to happen here. Your hydrochloric acid had a volume of 2, your sodium hydroxide had a volume of 2, but when you add the volume of hydrochloric acid as well as the volume of sodium hydroxide, both of them are now going to give you a volume of 4. So now what you have in this flask is you don't just have a volume of 2 of hydrochloric acid, you've now got a total volume of 4 cubic decimeters because you've combined your hydrochloric acid and your sodium hydroxide into one. The very same way that you see that the moles of hydrochloric acid and the moles of sodium hydroxide are combined into this one flask. Right, now we go to the next step. Cool. Now we need to look at how do these react with each other. How will you know how they react with each other? There's a reaction. It's right there. It's written. And this reaction tells you that they react in a ratio of 1:1. Meaning for every 1 mole of hydrochloric acid, 1 mole of sodium hydroxide will react with it. Let's see how that happens. We do a mole ratio, right? We say, okay, here the ratio of hydrochloric acid to the ratio of sodium hydroxide is basically 1:1. Now guys, mole ratio is going to be so useful in this entire thing. Very, very useful. But let me show you in the form of a picture first. Remember, we want to find the pH of the final solution. Emphasis on final. But before we get there, we need to talk about what is final. Which one is going to be left over? Which one is going to be completely used up? Mole ratio goes into that. But in the form of a picture, let me show you how this happens. The ratio was 1:1. Right? That means 1 HCl reacts with 1 sodium hydroxide to form 1 sodium chloride as well as 1 H2O. Again, 1 HCl, 1 sodium hydroxide is then going to form 1 NaCl as well as 1 water. Right. Now, what do you see left over? HCl. So from this, if we were lucky enough and could draw it all the time, we could say HCl is in excess. And how much is in excess? We've got 1 mole of HCl is in excess. And that means sodium hydroxide is the limiting reagent, if you could draw it. But guys, we need to show it in the form of a calculation. So let's do that, right? Let's create a hypothetical scenario. Step 1 is you need to solve what is the limiting reactant. That is the first step, because that way you'll find out which one is finished, which one is left over. Then in the final solution where you need to find the pH, you will know what is in the final solution, what is left over in that final solution. Is it the acid? Is it the base? Right, so let's solve for limiting reactants. If you remember, for limiting reactants, we need to create a hypothetical scenario, meaning we have information about 2 things. We know about HCl. They told us we've got 3 moles of HCl. We know about sodium hydroxide. We know that we've got 2 moles of sodium hydroxide. In an ideal situation, in a complete neutralization, when you guys see the word complete neutralization, what they mean is that when you've got HCl, let's say you've got 3 moles of HCl, right? Here's your 3 moles of HCl. And your reaction between HCl and sodium hydroxide tells you that they react in a ratio of 1:1. So what that actually means is that if you've got 3 moles of HCl and the ratio is 1:1, you would need 3 moles of sodium hydroxide to do a complete neutralization reaction with HCl. Because guess what would happen here? If you had 3 moles of sodium hydroxide, which we don't though, if you had 3 moles of sodium hydroxide, that one reacts with that one to form sodium and water, sodium chloride and water. That one reacts with that one to form sodium chloride and water. Another one reacts with that one to form sodium chloride and water, and eventually complete neutralization reaction. It is finished. There is nothing left over. That is an ideal scenario. That is what we'd like. So step 1 is basically you creating an ideal scenario. You can't do pictures, right? So create an ideal scenario where you say to yourself, you take one of the reactants and you say, if I have, or say since I have, right? Because you do have this much. Say, since I have 3 moles of hydrochloric acid, right? How many moles, you can even write it for yourself. You can say, how many moles of sodium hydroxide would completely react with it? We're just trying to find out in an ideal situation, how many moles would completely react with it? So how many moles of sodium hydroxide? Then you do a ratio. Remember, mole ratio is very important here. You say the ratio of hydrochloric acid to sodium hydroxide is 1:1. So since I have 3 moles of hydrochloric acid, how many moles of sodium hydroxide? And guys, you can even label it and say ideally, how many moles of sodium hydroxide ideally would I need? And you'll see that ideally for a complete reaction, you'd need 3 moles of sodium hydroxide. But then you take your ideal moles and compare them to your actual moles of sodium hydroxide. How many actual moles did they tell you about in the question? You've got 2 moles, 2 actual moles, meaning you don't have enough. Ideally, you want 3 for a complete reaction, but you've only got 2. What does that mean? It means that your sodium hydroxide is not enough. You do not have enough for a complete reaction. So your sodium hydroxide is actually going to limit your reaction. And that's why we end up saying your sodium hydroxide is going to be the limiting reactant. It will limit your reaction because it doesn't allow for this to be a complete neutralization reaction. All right.